Hi folks, so I'm Nic Bellinger, co-founder and CTO of Datera, and I'm also the creator and maintainer of the LIO target, which is the Scuzzy target subsystem in the Linux kernel. I'm going to talk today a little bit about the distributed placement implementation and kind of what influenced that from some of the higher level abstractions that Ashok talked about in this system in terms of policy and application intent. We're also going to talk about one simple and a little more complex example of how a placement map can change. One of these is the case with the disaster cache, where essentially we can have a two-way replica. One node can go down, but we can continue to maintain a quorum of writes. The second is a more interesting case where we can add to the cluster a all-flash node and then rebalance to put one of the replicas from an existing hybrid volume onto the all-flash volume based upon application policy. Beyond that, if we have enough time, we can talk a little bit about Datera's custom backend protocol, which is a two-phase write scale-out protocol, custom to Datera, and touch a little bit about the mesh rebuild capabilities. So I wanted to go back to the point that Ashok mentioned about having these higher level constructs in the system. Specifically, the ability to define the application requirements at a high level in the Datera policy engine and control plane applies those constantly to the data plane based upon the physical resources available in the system, right? And so that drove a lot of the design decisions in terms of data placement. The number one idea because of that design is the only constant is change. So the ability to change the metadata layout, the placement map on the fly happens all the time, right? The second one was that when we make these changes to the placement map, it cannot be disruptive to I/O. Now, there can be some impact on performance, but that can be controlled on a per application, per policy basis. And the second one is because of a scale-out system where you typically start small in the terabyte range and move into the petabyte range, the amount of metadata we have to keep a track for the placement maps can't overwhelm the system. So the granularity that we've chosen for the placement map, which is kind of highlighted here, and this is, in a very small context, essentially a single volume, is 16 gigabytes. And that is a nice trade-off between, as you go from terabytes to petabytes, we're talking about hundreds of thousands of objects to track in the control plane versus millions and tens of millions. But at the same time, it's small enough that when we do this mesh rebuild, walking the entire namespace within the volume, we can break those up into multiple processes and do the repair across multiple nodes. So far, in terms of getting to single-digit petabyte ranges, this has been the best granularity that we've picked. Beyond that, a lot of the storage systems, that are designed by low-level protocol guys like myself tend to focus on the I/O path, and the control plane and the application intent kind of comes at best second or third. We inverted that. The ability to define these high-level constructs on systems really is what influenced the design of the I/O path. And just to kind of talk a little bit about some of these components, mentioned the LIO target in the upstream Linux kernel. And of course, in the upstream Linux kernel, we have every protocol you can imagine.
There's no fiber channel over Token Ring.
I haven't been in storage as long as you have, Howard. And so the ones we decided to productize were the traditional iSCSI and iSer. Still, in these cloud installations, people just want normal TCP, and they're still kind of a little allergic to RDMA. So in practice, the deployments have been almost exclusively iSCSI. We took a couple years, preceding Datera to actually implement FC target mode. In the cloud world, that's a pretty hard sell. I mean, basically, it's Ethernet. So I got my first gray hairs from getting the fiber channel target mode into the Linux kernel, but aside from that. So we have the target here, and this is, again, just our vanilla upstream target that we've contributed to the kernel. And here we have the DSS proxy, and within that span placement information. Now, the simplest example we have here is basically where, let's say an LBA falls within that first 16 gigabyte range, and let's say in a two-way replica, it goes out to these servers. Now, one important thing to highlight about the architecture itself is that this is one node, right? So every node is self-contained, right?
So the placement map for every volume is replicated across all the nodes?
So the information is present within the control plane, And based upon the availability of the nodes themselves, that volume can move to another node. And so essentially, the control plane is a distributed database of objects. And each node can register to get callbacks when, say, a node goes offline. And then actively, that placement map can change based upon the availability of the individual nodes. But really, every node is self-contained. Every node contains the LAO target, contains the proxy, contains the placement information, and contains the server with the DIMMs, the flash, the SSDs, et cetera. So to tie it to a specific example, I want to focus on, let's say, just one of these spans, one of these placement maps. And it looks something, like this. And so the example we can talk about is a two-way replica with a disaster cache. And we'll call this the active map. And below this, we have the future map. And so let's say within a two-way replica that we have highlighted here, first one is server number 1, number 2, and these are both in an active state, right? And then we have a third server that is in reserve. And so in the case where we have a two-way replica and one of these servers, for whatever reason, goes away, this state, as notified by the control plane, goes to failed, and the server in the extended server in the active map goes to write only. And this usually happens within a couple of seconds based upon which agent in the control plane detects the component or the node failure first.
So you predetermine where the failure is going to land?
We have a standby server that can start accepting writes in the point in which one of the initial mirrors fails.
Yeah.
Okay. So.
Yes.
So
And it will ultimately be rebuilt on that server?
That's correct.
Yeah.
Yep.
Yeah.
So at the point in which we have two active mirrors now after the initial failure, this one remains read-write and this one remains write-only.
Okay. In the event of multiple node failures, don't you run the risk of overloading some of those pre-selected? I would want to choose where I'm going to put the data after a failure based on knowing what's left after the failure.
Yes. So the server, this placement map is actually done based upon utilized capacity within the system. And that can actually change. So for example, we could start out with server number 3 in the extended map, but we add a fourth node to the system that has 0 utilized capacity. And the system can rebalance itself to change the extended server to reference the node that has no capacity versus one that's, say, overloaded.
And let's say that server 3 dies as well as server 2, then you could change it to, say, server 4 or something like that.
Yes. Yes.
Okay. And the clock on that is seconds, minutes, days?
Seconds.
Okay. I'm satisfied. Go on.
Yep. And so as this node comes back online, but before it's actually repaired, it goes into write recovery. So this means that all new incoming writes from the iSCSI target are now going to 3 mirrors. And at the same time this is happening, our data op, which is the mesh rebuild client, starts querying all of the nodes based upon all of the spans for the particular volume, and rebuilds in the background on the fly while it's accepting new writes.
What's the clustering mechanism?
For the election of the control plane?
For knowledge that a server has gone down?
Sure. So we have agents for individual services and components within the system that can either, say, put the node into a degraded state or mark the entire node offline. So let's say, for example...
It's not just Heartbeat, though, over IP. It's actual Linux-based services that are monitored and...
Yes, so it's all Datera's specific agents that look for health of the hardware itself. So for example, the individual nodes can withstand multiple hard drive failures. They can withstand one flash failure, assuming that there's 2 flash drives or 2 NVMe flash devices in the system. Or if the NVDIMM fails, then we mark the entire node offline.
Are those tunable?
Not externally, no.
Okay.
And so the key aspect that allows this mesh rebuild to happen, where the node that failed is recovering all of the missed writes, while at the same time accepting new writes based upon the span within the placement map going into write recovery mode, is that the Datera data store itself is time-based, and it can accept new writes with an updated timestamp. But older writes never overwrite the new writes that are in flight. And that is the key reason why you can have these new IOs happening at the same time you're actually doing data copies for writes that were missed when the server was down. And because it is an augmented time-based data fabric, when we're doing that comparison, walking through all of these spans for the particular volume, it's only comparing the latest timestamps. It doesn't actually have to look at the payload of the data. And it's actually a one-pass system, too, because of the nature of that data store being able to always accept writes with a newer timestamp and not overwrite regions with an older timestamp. That makes sense. And so, in the point in which,
Does every node require NVDIM?
So in the appliances Datera ships, we ship with NVDIM on the Supermicro platform. We also support an NVRAM card for the software SKU. We do have some POCs that are running with NVMe flash, block addressable flash, in place of the NVDIMMs. There's certainly a performance hit when you use block addressable NVMe versus byte addressable NVRAM or NVDIMMs. But some customers have requested that.
And support for HPE's persistent memory NVDIMM comes
JEDEC.
when some what's that?
The JEDEC stuff, yeah.
Yeah, that comes when some customer demands it.
We actually have been working on it for the last month or two.
Okay.
To the point where it's, say, alpha quality.
Fine.
But there hasn't
So-
been any customer demand so
Yeah.
far, specifically for HP systems.
And Howard, just on that, yes, we have HPE with that in the lab. That's actually, those are very good systems, and we actually also have Intel 3D Crosspoint in the lab now, which is another alternative for that.
Now I'm jealous.
Really?
Yeah.
I thought I'd mention it.
Sticky finger.
I think we should go see the lab.
Yeah, we got to
Don't let
go
him
see
anywhere
this
near it.
lab.
And so obviously that's been one of the drawbacks, because the system is optimized for byte addressable memory. But of course, I would say that's maybe the one not quite commodity part in the system.
But it's coming much more common.
Yeah, and I mean the Skylake systems, separate from the 3D exploit memory themselves, have integrated in the BSP that ability to do byte addressable NVDIMMs.
Yeah.
We don't no longer have to go to a third party for BIOS modifications and all that other
Yeah,
time-consuming.
it was
stuff.
ugly, and it's getting much less ugly.
Yeah. Okay, and so really to complete the example, once this mesh rebuild one pass recovery completes, essentially this node goes back into active state, and this goes back to reserved, and we send out discards for the disaster cache to drop all of the writes that we were maintaining when the node failed.
I'm sorry, what were the checkpoints that were required in order to make the determination that server 2 was back up and viable?
Yep. So, when the server itself is functional and comes back online, we put it into this write recovery mode so that new writes are being accepted.
Right.
And at the same time, the one pass mesh rebuild starts walking the entire namespace of each one of these spans within the placement map and starts doing comparisons based upon timestamps to determine the writes that it's missed, and then starts copying those from multiple nodes, including the disaster cache on the third node that came online at the time of the failure, to copy those back. And so once it walks the entire namespace of all of these spans within the placement,
And every
then it knows
block
that it's
is
able to
consistent.
translate from.
So it's
Yeah.
purely a data state issue, though. When every block is now consistent, then it brings it back to an active state.
Let's say based upon metadata, based upon timestamps. So it doesn't actually have to examine the data itself, but just based upon the timestamps for the writes that were missed upon failure. So it makes it very fast in that sense.
Do you assume that all the data on the recovered node is bad, or are you doing some kind of checksum to
No.
leave the data in
Just getting
place?
rid of the stuff that's written.
These
So
are
the
timestamps.
writes that were missed at the time in which the failure happened. Now there is background scrubbing as well to, let's say, catch silent data corruption on.
Okay, so you assume that anything that was on the node when it crashed is still there?
Yes, and it will verify that based upon those timestamps.
Yeah, no.
Yeah. So if any timestamp happened that's later on another node, it will do that
Okay,
data copy.
but that minimizes the amount of data that you're going to replicate. And yeah.
Exactly.
Do you have nodes that typically go out of the network and come back in on a transient basis like this? I mean,
Sure.
Yeah, because I did a firmware upgrade.
Absolutely.
On the server.
non-disruptive upgrade, so to speak.
So yeah, well, I mean,
No, it's up to the
it's, if
cluster,
you have a
not
big
to the
enough,
node.
if you have a big enough cluster,
Yeah.
No, it's
then
not disruptive to the cluster,
disruptive
not
to a
the
node isn't. Yeah.
Yeah. And because that mesh rebuild can happen in the background, that's fine. Again, if
Yeah.
we just have
No,
nodes
this
that go back and forth.
this is what I want for
Yeah,
white
it's
box
built for
servers,
failure.
because I'm going to take them offline for an hour twice a year to do that firmware upgrade or something.
Absolutely.
Built for failures like that.
And the other benefit of the mesh rebuild is that the more nodes we have, the more nodes that we can read from and compare against, and the faster the rebuild becomes.
Right, because 16 gig pages are distributed across all the nodes, and so it's a many-to-many.
Absolutely. Yep.
Okay.
Okay, and so
But that's 16 gig pages just for distribution, right?
that's correct. Okay, so let's go to a little more interesting example. So let's say we have this 3-node cluster a customer bought to start, and hybrid nodes, right, with MLC flash and HHDs. And at some point, they realize they have an application that they want to start to avoid, let's say, the tier 1 penalty seeks coming from HDDs because their working set has increased. They didn't anticipate. So we can add an all-flash node. Now, back to the placement maps. So that design requirement, the only constant is change. So we go back to the active placement map and the future map. And so again, we have servers 1, and let's say this is a 3-way replica. And at some point, using these high-level constructs that Ashok mentioned, we can take all of those bound instances provisioned from the templates and say, put one of the replicas on the all-flash node. So the way that works from the perspective of the placement is that now we have a future map that has server 1, server 2, and server 4. And so when a new write comes in, it will look at both the active map and the future map. It'll see that it shares 2 nodes, so it only has to do a write to both of these once. But then it does a write to node number 3 and write to number 4. And so this goes into write only. This remains in RW, 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 RW. Now, the speed of the mesh migration can also be controlled on a per application policy basis. Now, typically this happens pretty slow. Let's say 5% or 10% of the performance is what we use for the default. But certainly if you're under extreme pressure and the working set's large enough where you're continuously missing an HDDs, that's a knob that can be turned by the user to increase to decrease
It's Sophie's
the time.
choice.
Yep. And so the same thing happens. Just like with the mesh rebuild, the AFN queries each of the spans within the placement and then starts getting data copies back. And so for each of the replicas on each of the existing nodes, it starts to move data around. And as new writes come in, they continuously go to node number 4, but still this remains in write only until the mesh rebuild walks the entire number of spans within the volume and moves all of the existing writes to the all-flash node. And once that happens, essentially we swap the future map for the active map. And now this becomes node number 4 and in read-write state. And everything else goes away. And so really this idea of an active map and a future map that can both accept new writes on the fly, but at the same time do the mesh rebuild in the background, allows us to constantly being able to change that placement with very low overhead. And because the system is designed from this perspective of these high-level constructs in the control plane, attempting to always be optimizing to meet application intent based upon the physical resources, it makes it very easy for folks to get high utilization out of the physical resource that they have in the cluster. But also being able to add new nodes in the cluster, being able to decommission nodes. And really, what falls out of the design of the system is the ability to absorb both new x86 hardware platforms and new media types and use that control plane to dial in the application to be balanced or to be utilized on these new technologies. Any questions?
So can you preferentially treat the all-flash node for read activity, or is that, how do you get the performance out of the all-flash node if it's just another one of these replicas?
Absolutely. So within the DSS proxy, we can say, in the typical case, we want to favor local reads, right? So we don't have to take the extra network hop. Now, once we add an all-flash node into the mix, we can say, okay, this particular server, server number 4 here, we should prefer reads over to here. So this is something that the control plane sets within the DSS proxy based upon the placement information to prefer either a local read to avoid the network hop or to an all-flash node once we know a particular replica has been migrated to the all-flash node.
And you'd do the same if I have replicas on flash and on disk, you'd preferentially read from the flash.
Yes. So if there's no flash, it'll always preferentially read from the local node, but if there is flash, even if it's a remote hop, it'll always read from the remote flash node. Absolutely.
So how does the data placement map in a hybrid node whether the data is on flash or on disk?
So through an additional bit of metadata that's not represented directly in the placement map, but is set within the proxy on a per volume basis, basically to say which node it should be preferring. And then each node has a type of whether it's hybrid or whether it's all flash. And then we make that decision at the lookup time when the I/O comes through and looking at the placement maps about which.
And the hybrid nodes, does the data migrate from flash to disk on a cold basis? I mean, is that tiering?
It does. So that aspect, it's still relatively simple in the sense that all of the writes are destaged from the NVDIMM until the MLC flash, but the acknowledgement goes back to the host the minute it hits NVDIMM.
Well, that's why you have NVDIMMs.
So to mask the latency. So basically it's just the network latency going to each of the nodes and the replicas, the commit into the NVDIMMs and the acknowledgement back. So once it's destaged from NVDIMM into MLC flash, we can actually take our time and absorb it into large erased unit sized writes to get nice performance and avoid, write amplification, all that stuff. So in the background, it does begin to destage into HDDs into even larger, I think 8 megabyte size writes. Now, when we miss into tier 1, it actually gets promoted back into the MLC flash first, and then gets served from the MLC flash. So the implementation is still pretty simplistic in the sense that we don't propagate the policy all the way down to the tiering subsystem to say, pin this particular application's read so they're always coming out of cache. But that's something that we're working on for a future release.
Okay, and the migration up and down is in 8 meg pages in real time?
So the writes destaging down are 1 megabyte into flash, 8 megabytes into disk, and it's I/O sized, I want to say, coming back up from HDD into flash.
So if I'm running an application doing 4K IOs, you're going to promote 4K?
That's correct.
Cool.
And
That complicates your metadata, but that's your problem.
Yeah. And we usually do about 6% of flash versus disk. So like 6
dedupe
terabytes
complicates
of
the
flash.
metadata at that same granularity too. So 4K is here to stay.
Yeah.
Dedupe complicates metadata at 4K granularity essentially. Because
Right.
you do-
Yeah. It,
Right.
actually,
So therefore you
it
have-
leaves you prepared.
You
Yeah.
have to be able to handle metadata at that granularity.
Yeah. Yeah. No, I was thinking more about the variable size than the 4K. But you're right. Once I don't want you to dedupe at 64K anyway.
I believe Howard just acknowledged he made a
Okay,
mistake.
so that's kind of the basic overview.
Okay. So how do we expose all this in terms of QoS or priorities or however?
So the current product does rate limiting based upon bandwidth and IOPS on a per volume basis. Essentially at this point here between the target.
So your
and-
QoS is a throttle.
Initial, it's rate limiting. We're moving to provisioned IOPS based
you say
upon
fraud?
the total number of IOPS.
Throttle,
in the
not fraud. I wouldn't say fraud
Okay.
unless it actually was a fraud.
All right, my bad, my bad.
Frog, not fraud.
So the one I would say, beyond the simplicity of the rate limiting QoS, the one nice thing about it, as Ashok alluded to, is the ability to abstract it into those higher level constructs. So if you make one change to a QoS within a volume, within a template, it affects all of the provisioned instances.
Yeah, but okay.
And so that's kind of it. Like I said, a lot of the folks, hardcore storage protocol people tend to think about things specifically from the I/O path. And I think we've done a good job of balancing.
Data placement is more significant, especially in a hybrid system. And for as long as I've been watching the storage business, there's always, in every generation of vendors, there's one who makes the mistake of looking at it as a network problem.
Yeah, I believe that.
Nick, there's a question from Twitter regarding encryption. Where and how?
Yep. So in the 2.0 product, we're supporting at-rest encryption using self-encrypting drives on the AFN, and then using software down to the nearline SAS HTTPs. This has been the one asset we've gotten from cloud folks so far, and specifically being able to do some of the encryption on a per-tenant basis. As is, there's no in-transit encryption. That's something we've kind of considered looking at adding, but so far hasn't been a hard ask from folks. So just at-rest encryption for the 2.0 product.
It's done on a volume by volume basis.
So as it currently is, it's encrypted using SEDs, which is basically blanket encryption across the entire drive. The software encryption that we're moving to allows you to encrypt it on a per-tenant basis.
What about the KMS?
TMS?
Key management.
Key management system?
Oh, so far that's basically putting the keys inside of the control plane. So very, very simplistic. I mean, nothing like IKE or any of the more interesting things that you
Does it
need.
support external KMS system?
Very basic stuff.
Can you support NVMe over Fabric?
Oh.
It's
So
right up there on the board.
It was. So spent some time in the working group and got a, let's say, alpha implementation. Right now, by virtue of the hard requirement for RDMA, it's pretty much a non-starter for almost everybody. So that's something we could, demo. We probably intend to demo in the next 6 months or so. But as far as customer interest, it's been zero. So we'll see if it moves beyond kind of just a bunch of flash, workloads. I mean, I think that's where most of the folks who are making new ASICs are kind of focusing around.
Yeah.
But the thing that some of them miss is, they're doing all these interesting kind of hardware tricks where you mess with the completion queue pointers, where you never actually have to go to the host CPU, which makes it extremely fast. But at the same time, it makes it very difficult to actually put snapshots or scale out or any of the other data services behind it.
Gee, we were saying things like that just the other day.
So we'll see where NVMe or where Fabrics goes. I mean, what they should have done is just took the Scuzzy command set and then put it in this new protocol instead of rewriting everything and not having copy offload and not having all these other features that Scuzzy's had for a decade or more. So we'll
Yeah,
see.
but if they did that, people wouldn't have taken all the cruft out of their code, and
That's fair.
forcing it to be completely new meant it has to be fresh.
But then again, in the Linux world, one of the things that we've been working on the last couple of years is the original prototype for Scuzzy MQ, which was the generational rewrite of the IO stack in Linux. And all of the NVMe over Fabric stuff happened before Scuzzy MQ existed. And of course, once all the vendors measure block MQ with NVMe over Fabrics versus Scuzzy MQ with ICER, there's no difference. So it's no longer a software overhead, at least in the Linux world. Other operating systems may be a different case.
Yeah.
But I think we've fixed that problem in terms of, let's say, memory level IO performance using RDMA. There's no difference in the Linux kernel anymore.
Well, that could get really interesting. Of course, you can't run ICER on VMware anymore, but that's
So we'll see.
That's a problem down the road.
Yeah, I mean, especially with things moving to L3, like Ashok alluded to. The L2 RDMA value prop is getting harder to kind of justify. And with Skylake, the platform, Lewisburg, offering iWarp NICs built in, you may finally see an uptake in iWarp after all these years. And maybe ICER and NVMe-OF will get a new life because of that, hardware just showing up in every server.
Yeah, although I see a lot of layer 3 on the front end. I don't see layer 3 on the storage side.
Well, it depends. I mean, the biggest reason why folks have asked us for L3 is being able to expand that failure domain across racks. We can extend a cluster across racks. So if that's not a hard requirement or you can use L2 tricks to do it, then
Yeah.
I would agree.